In this video, we're going to look at experiment 18, which focuses on determining the KSP of a weakly soluble salt. So this is actually something we've been doing in our virtual lectures while you guys are in lecture, quote unquote. So if you have any questions about KSP, you should review for this video the video that is titled "Determining the KSP from the Equilibrium Concentration," or determining KSP from concentration values, because essentially this experiment is exactly that. So a couple of things. So the weakly soluble salt that we're going to be working with today is called silver chromate. So the stoichiometry is that there are 2 silver ions to every 1 chromate ion, and this is a weakly soluble salt. So one thing that I like to focus on at the very beginning of the experiment is to think about what's the difference, what makes something soluble versus insoluble, quote unquote. As you guys have been listening to your videos in lecture, you know that all salts are soluble to some degree, meaning whether it's soluble like sodium chloride, where you can put many grams into a solution of 100 mils of water, or it's quote-unquote insoluble, we know that there's a little bit of the salt that will dissolve. So whether it's a small amount or a large amount is what's going to separate a soluble salt. Many grams of the salt will dissolve, and an insoluble salt, typically this is a tiny fraction. And normally the cutoff for solubility starts to be at around 1%, right? So anything that's over 1 to 2%, you might consider it to be somewhat soluble. Anything less than 1 to 2%, you generally consider that to be insoluble. So when we say that silver chromate is an insoluble salt, what we're really saying is that it's very weakly soluble. And then the next question is what can we measure experimentally to determine the KSP? So we have to write the KSP expression for this. And we know that when we write an equilibrium constant, we're going to take the concentration of the products, silver and chromate, and we're going to take each one of those and raise it to the power of the coefficient. So we get an equation that looks like this. We get silver ion squared, and then we get the chromate ion to the 1 power, because there's just a 1 there. Now we exclude the solid on the bottom because we don't include solids since their concentrations don't change. They're basically a constant. So what do we need to measure in order to determine the KSP? Well, we would need to know the concentration of either silver or chromate at equilibrium. Because if we know one, we can get the other. And I'm going to show you how we get the other in just a second. We're going to use an ice table. So we need to be able to measure one of these 2 ions in solution at equilibrium. Okay, so our goal today is to determine the equilibrium concentration of the chromate ion. So to give you a sense of what silver chromate looks like, this is a test tube with some solid silver chromate in it. You can see that it has this nice red color to it. So when you put silver chromate into water, what's going to happen is at the very beginning, and we're going to create an ice table now, at the very beginning of the experiment, when you first put the silver chromate in the water, the salt hasn't had a chance to dissolve at all. So we start with 0 molar and 0 molar. And then we're going to, over time, as we equilibrate, we're going to add some silver and we're going to add some chromate. And the amount that we add is going to be in a 2 to 1 ratio. And we know that from the stoichiometry. There are 2 silvers for every 1 chromate. So that's where I got the 2 and the 1. So at equilibrium, we're going to have silver plus as 2x and chromate as x. And x in this case is going to equal the concentration of chromate. So if we know the concentration of chromate, if we're able to measure that somehow, then we also know the concentration of silver, because whatever this concentration of chromate is going to be, the concentration of silver will be 2 times that concentration, or it'll be twice as concentrated. So we can plug these values from equilibrium into the KSP expression, where we have 2x squared and we have x. So now if you do that carefully, if you do 2x squared, we have to square the 2 and we have to square the x, so we get 4x squared. And then we multiply that by x, which gives us 4x cubed. So if we know the concentration of chromate, again, we know x, and we can therefore get the KSP. So that's why our goal today is to determine the equilibrium concentration of the chromate ion. Okay, so how do we make this weakly soluble salt? So the first thing that we're going to do is we're going to start with nothing, and then we're going to make our weakly soluble salt. So we have to prepare the salt that we're going to study. So we're going to use a metathesis reaction to prepare the silver chromate. And what we're going to do is we're going to combine silver nitrate with potassium chromate. When these two combine, they're going to exchange partners in a metathesis reaction, and they're going to make silver chromate, which will precipitate as a solid. We know this because silver chromate is quote-unquote insoluble or very weakly soluble. So if Q is greater than KSP, meaning our concentration of silver and our concentration of chromate is greater than the value of KSP, we are going to make solid silver chromate. And then the other thing we'll have in solution is some excess potassium nitrate. And we'll get rid of this by washing. So let's take a look and see what this reaction looks like. So what we're doing now is we're dropping some potassium chromate, that's what's in the pipette, into silver nitrate, which is in the bottom. And you can see that as you combine them, the ions react with each other to make that red solid precipitate that you can see here. Now I want you to notice one thing. The chromate solution in this case has a yellow color to it. It's a little hard to see, but you can actually see there's a little bit of yellow coloration. That's going to be very, very important to how we're going to figure out the chromate solution concentration. So when you would do this experiment in lab, you would literally do this. We would add 5 mils of the chromate solution, 5 mils of the silver solution, and we would make the solid precipitate. So in lab, what you would actually physically do is you would take 5 mils of 0.004 molar silver nitrate and 5 mils of 0.0024 molar potassium nitrate, and you would combine them together into one solution, causing your precipitation. So one thing that's a good thing to do is to figure out what is our limiting reagent here. So we need to have twice as much silver as we do chromate. That's because the ratio of silver to chromate in silver chromate is 2:1. So if we look at the volumes, our volumes are the same. So we know that we would need twice as much potassium, we would need twice the concentration of silver as we would the potassium chromate. So in this case, what we see is we have 0.0024, so we have a little bit more than 0.002, which is what we would need to be stoichiometric, right? So half of this would be 0.002. So the excess reagent in this case is our potassium chromate. We have a little bit more than the 0.002 that we would need to make it stoichiometric. The reason why we do this is because the silver is more expensive. So we want to make sure that all of that silver gets precipitated by the chromate. The other reason why we do this is to make sure that we can wash away the, when we wash this, we can make sure that we wash away the chromate, which is easier to wash away than the silver. Okay, so the next thing you're going to do is, so once you've made your solid, you saw that nice bright red precipitate form, we have to isolate it and get it pure. So to wash the precipitate, the reason why we're going to wash the precipitate is to remove this excess potassium chromate. So the way that we're going to do that is through the process that you guys are familiar with using a centrifuge. So you're going to put the raw product, which is the precipitate and the supernatant, into a centrifuge and spin it down. And then this will separate the solid from the supernatant, which has the excess potassium chromate. The supernatant is discarded. That's going to get rid of that excess potassium chromate. And then you're going to add fresh NaNO3. So we're adding some fresh solution that has no potassium chromate, and we're going to wash this to get rid of anything that's an impurity. And then we're going to repeat this a couple of times. So we're going to centrifuge, add fresh NaNO3. Centrifuge, discard the supernatant, add fresh NaNO3. We're going to do that 2 more times until we've washed it for a total of 3 times. Now, one thing that you should note, the reason why we're doing this in silver nitrate is to maintain what we call a similar ionic strength. We need to have the chromate in a solution where we can control the amount of ions that are around it. It has an impact on its UV-vis spectrum, and we're going to talk about that in a second. So we want to make sure that the conditions by which we measure the chromate are the same for when we do our calibration curve and when we do our experiment with the weakly soluble salt. So that's why we have the NaNO3, and we'll talk a little bit more about that when we get to the calibration curve and the determination of the weakly soluble salt concentration. Okay, so now for the most important step. Once we've washed our potassium chromate, we have to measure. We have to let it form an equilibrium mixture. So what you're going to do is you're going to take that solid, you're going to disperse the solid into NaNO3 and allow it to sit for 15 minutes. And the reason why you allow it to sit for 15 minutes is we have to allow this equilibrium to establish. We have to let the silver chromate dissolve, forming the equilibrium concentrations of silver plus and chromate 2 minus. So that's the most important step of the entire process, in addition to washing. So when this process is done, we're going to have two things. We're going to have a precipitative silver chromate at the bottom, and then we're going to have a supernatant, which contains the equilibrium concentration of silver plus and chromate ion in solution. Now this picture is probably a little exaggerated. The solution would not look this dark, but it would have a nice yellow tint to it, a very, very faint yellow tint, which is the chromate ion that's absorbing light. So the supernatant is what's going to contain the equilibrium concentrations, and this is what we're going to use to measure that chromate concentration. So now that we have our supernatant, which has the chromate concentration at equilibrium, which is what we need to get KSP, we have to come up with a way of measuring that concentration. And the way that we're going to use that is through UV visible spectroscopy. This measures the concentration of an aqueous analyte by its absorption of light. So the instrument that we use in lab, this is a picture of it. This is the spectro-vis plus, and this is a plastic cuvette which holds our sample. So this cuvette is just a nice clear plastic container that's a square container in this case, where we can shine light through it and measure the absorbance of our sample. So how does a UV-vis spectrometer work? Well, inside this box you have a light source, and this light source makes UV invisible light. And there are two light pathways through the box. One is the sample pathway, which is down here, and the other is the reference pathway, which is up here. So the reference pathway, basically the detector, we have a detector, it's a diode array, which basically what a diode array is, it's a whole series of these diodes that can measure light at different wavelengths. So we can get the entire spectrum of visible and UV light in one go with a diode array detector. So the way you can think of this is it's very similar to our eye, which when you look at something, you can see all the colors at once and their relative intensities. Except this eye is programmed not only to look at this qualitatively, but also to look at it quantitatively. So the reason why we have a reference detector is to measure the output of the light. We have to know how much light this source is making. So that's what the diode array detector in the reference line does. In the sample line, we put our cuvette into the sample line, and this cuvette which contains our sample, will absorb some of the light. So you'll notice that the light going in is a little bit less than the light coming out of the cuvette. So this diode array is going to see some amount of light that's attenuated by the sample. So we can calculate from that what's called a percent transmittance, where we take the light that comes in, the intensity of the light that comes in from the sample array, and we divide it by the light that comes in from the reference array. And then by doing that, we get a percent transmittance. How much of the light that was shined upon the sample actually came through? And then from there, we can calculate what's called an absorbance, which is where we take 2 minus the log, this is a log base 10 of percent T. And the way this works is as follows. So if you have an absorbance of 0, then your percent transmittance would be 100%. So if there's nothing absorbed, you get 100% transmittance. If you get an absorbance of 1, then the light transmitted is only 10% of the original light. So an absorbance of 1 means that 90% of the light was absorbed. If you have an absorbance of 2, this means that 99% of the light was absorbed. If you have an absorbance of 3, this means that 99.9% of the light was absorbed. So because this is on a log scale, the percent transmittance continues to go down by an order of magnitude with every absorbance unit. So basically what absorbance tells us is how much light was absorbed. The higher the value of absorbance, the more light was absorbed. The more light was attenuated by the sample. Okay, so using that experiment, what we're going to do is we're going to take a feature of UV-vis spectroscopy that will allow us to correlate the concentration with the absorbance. There's this thing called Beer's law. It's an equation where we have absorbance on one side and we have the concentration on the other. And this makes sense because if you think about it, as you make a solution more and more concentrated, you can think about a cup of water putting food coloring in it. If you put 1 drop of food coloring, it looks a little bit green. 2 drops, it gets more green. 3 drops, it gets even more green. By the time you put in 4 drops, it might even be hard to see through the sample because it's absorbing more and more light. So absorbance will always track with concentration. And this is a linear relationship, and it depends on 2 variables. The relationship depends on the extinction coefficient, which is a parameter that depends on the analyte. In this case, it would be chromate. So different analytes have different extinction coefficients, and the path length. So the way to think about the path length is the thicker your sample is, the more light it's going to absorb. So we have to control for that thickness. Now, the nice thing about our cuvette is that it's 1 centimeter. So in essence, we can kind of ignore the path length because it's just a factor of 1. And that's why we make it 1 centimeter, because then this essentially, the L goes away. So the absorbance is really dependent on the extinction coefficient and the concentration. So here's what we're going to do. To get this extinction coefficient, we need this extinction coefficient because it will allow us to figure out if we have an absorbance and an unknown concentration of chromate. If we know that extinction coefficient, we can take that absorbance and convert it to a concentration. So to get the extinction coefficient, we have to kind of go in the reverse direction. We have to take a bunch of known concentrations of chromate, look at their absorbances, and figure out what the extinction coefficient is from the known absorbance and the known concentration. So the way that we're going to make our concentrations of chromate is we're going to take a stock solution. And the stock solution that the lab techs would have made would have been 0.00240 molar. Note the significant figures because that's going to be important. And then what you're going to do is to make a whole bunch of different solutions out of this stock solution. We're going to take some of that stock solution, we're going to put it in another volumetric flask, and then we're going to dilute to the mark with 0.25 molar NaNO3. Now here's where the concentration of NaNO3 comes in. As we make all of these solutions of different concentrations, the environment is going to be the same. Every single one is going to have the same concentration of NaNO3 in them. So that's important to keep in mind, and that will allow the spectrum of this to remain constant, meaning the peak in the UV-vis spectrum will stay constant. So essentially what we're going to do is we're going to take a bunch of different volumes, dilute them to the same amount, and then we can get a whole bunch of new concentrations. So the way that we're going to figure out the concentration of the diluted solution is through the dilution equation M1V1 equals M2V2. So if we started with 0.1 mils, and we dilute to a total volume of 10 milliliters, we can take our concentration of the stock solution times the volume that we use in the transfer, 0.1 mils, and then when we fill the volumetric flask to the mark, we're going to get a total of 10 mils. So from this, you can calculate the concentration of the diluted solution by dividing these two numbers by 10 mils. So we're going to do this 4 times, and we're going to make 4 separate solutions. One with 0.1, one with 0.2, one with 0.5, and one with 1 mil transferred into this. So you're going to repeat this process 4 times to make 4 different concentrations of chromate. So your job is to use this equation to figure out and fill in the concentrations of chromate for each one of those dilutions. Okay, so then we take those solutions and we stick them into the UV-vis spectrometer. So now let's look at what data the UV-vis spectrometer gives us. So if you remember what I said about it having a diode array, that diode array allows us to look at the entire spectrum of visible light. So you can see here this picture maps the color with respect to the wavelength and then where this thing is absorbing. So you can see that the chromate has very little absorbance above 500, almost zero essentially. And then below 500 we see a peak. And this peak is an indication, because the absorbance is going up, that the chromate is absorbing light. So the reason why the chromate looks yellow in color is because the chromate is absorbing the blue colors of the spectrum, leaving behind the green, yellow, and red parts of the spectrum, which give it that yellow color. So what we're going to do is we need to get the absorbance out for each of those concentrations. So what we're going to do is we're going to go in and we're going to measure the absorbance at different locations. We're going to go into a single wavelength at the peak. About 400 nanometers is where the peak is. And then we're going to pick out what is the absorbance at each one of those concentrations. And what you'll find out is that you get a nice linear relationship. Now, so just so that you don't get confused, this data is not the data that's in your experiment. I'm just using this data as an example. This was from another student's vernier setup. The data that you have is different, so don't try to reproduce the data from any of this. But anyway, it's the same idea though. So what you can see is you can actually see this linear function develop. As the concentration goes up, we get a sort of a linear behavior where the absorbance also goes up. And this makes sense because if you look at Beer's law, if you think of the absorbance as a y, the chromate as an x, and the extinction coefficient as the slope of the absorbance versus concentration line should give you the extinction coefficient. And in this experiment, we get an extinction coefficient of around 5,900. Yours will be slightly different from that, but close. So you can see from the UV-vis that we get the peak, the absorbance peak. We go in and we take the absorbance at the top of that peak, and then we plot that as a function of concentration. So now, in your case, you are welcome to make those plots if you like. If you know how to use Excel, and you want to use Excel to plot the absorbance versus the concentration, you can do that. There's one caveat, and that is that the line has to cross the zero at 0. So your y-intercept must be locked to 0. If you don't know how to do that in Excel, then don't try to make the plot in Excel. But if you want to try to make the plot and you do know how to set the y-intercept to be 0, you can do that. So the way that we want you to do it is, instead of making a plot and figuring out the linear regression of that plot, what we're going to do is we're going to take each one of these data points. So we have the absorbance for each one of these concentrations. You're going to take the absorbance and divide it by the concentration of chromate you calculate, and then get an extinction coefficient for each data point. You're going to write those here, 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 and here. And then what we're going to do is we're going to take the average of those four extinction coefficients to get an average molar extinction coefficient. So really it's very similar to the process of doing a linear regression in Excel. It's just that this allows us to do it without you guys having to worry about knowing how to use Excel. So that's that. So now if you do it this way, you just do your calculations, you figure out your concentration of chromate, you do your extinction coefficient is equal to the absorbance divided by the concentration. You write your numbers here, take the average, and then you calculate the standard deviation, and that's fine. If you decide to do it in Excel, you need to print out your plot and with the slope, and include that as a scanned image in your upload. But that's up to you. Okay, so now that we know the extinction coefficient, the average extinction coefficient, we can now relate, if we have an absorbance, we can now use that extinction coefficient to figure out what concentration we have in an unknown sample, which is what we need because our sample contains the chromate and we don't know the concentration of chromate in that supernatant, and we need to find it out. So you're going to take a little bit of this supernatant and put it into the UV-vis, and we're going to get absorbances. So the absorbance at 400 nanometers was 0.263, 0.285, and 0.267. Basically, we took took 3 portions of this solution and took the absorbance just to get an average. So now you guys, your job is to calculate the chromate concentration in the unknown. So like I said, we're going to use the extinction coefficient, and by dividing the absorbance by the extinction coefficient using Beer's law, we can get the chromate concentration, which you're going to write here. Now, if you remember back to where we wrote our ice table, once you know the chromate concentration, you also know the silver concentration, because the silver concentration is twice that of the chromate concentration. So you can simply take the chromate concentration and multiply it by 2 according to stoichiometry. Then when you want to calculate the KSP, you have 2 choices. You can either take the KSP equation, KSP is equal to the silver ion concentration squared times the chromate concentration. That's a perfectly fine way of doing it. Or you can simply take the chromate concentration and plug it into the KSP is equal to 4x cubed equation. So you can use this and this, or you can use these 2 and this. Either one, they'll give you the exact same number for KSP. And then so the last thing that you have to do is, once you have the 3 KSPs, you have to take the average KSP and the standard deviation. Now, if you guys don't remember how to do the standard deviation, there are a couple of examples in the book which you can look up. If you look up experiment 10 from the first semester, that should have the equations for it. Or the best thing to do sometimes with these things, if you don't remember, just simply look up on YouTube or Google how to do standard deviation, and you can figure it out. I think by now, being in second semester, you guys are pretty good at figuring these things out. So you got to calculate the standard deviation here, and also for your molar extinction coefficient. If you have any questions, you can contact your lab professors. This lab is going to be due during your normally scheduled lab, at the end of your normally scheduled lab time. And this will be during the week of, let me just take a look at the syllabus. So this is experiment 18. So this will be due during the week of 3:30 and 4:06, depending on your lab section. So keep that in mind and keep your eye on the syllabus.